In this video, we're going to talk about kinematics. Specifically, we're going to discuss kinematics in one dimension. So, to start off, what is the study of kinematics? Kinematics is an area of physics, specifically an area of mechanics, that describes motion. And so what we mean by describe is we talk about where objects are and how their position is changing, how fast, so how fast is something going in some direction, and then is it speeding up or slowing down, speeding or slowing. And when we get to two dimensions, we'll also consider it changing directions. But these are all ways we describe motion. What we're not going to do is answer the question why something is moving. So we're going to start all of our problems, all of our questions and our scenarios with things that are either already in motion, or we're going to describe how it's going to move. But really, if we want to get something moving or change its motion, this is the study of dynamics, which studies forces. And forces are the things that cause and change motion. Okay? That cause and change motion. So once we get a good grasp of kinematics, then we can move on to dynamics and learn why these things are happening. But for now, we just have to assume things are already in motion, and we're just going to describe it. Okay? So the first thing that we need to describe an object's motion is we need a way of knowing where it is. So this is called an object's position. And it's typically given by some x coordinate or y coordinate. Of course, in two dimensions, you would have both an x and a y coordinate. And it's usually measured relative to some origin or some zero position in units of length. So if I want to identify your position, so we're going to measure it in meters, I might say you are 2 meters from the origin. So if you have an x number line, maybe this is x equals 0, and your object is over here at x equals 2 meters away. That's how you identify where an object is. And by itself, the position of an object is not very interesting. What we really want is to get to the notion of displacement, which is the change in an object's motion. Or not motion, change in the object's position. So the object is in motion or has been in motion, and so its position is changed. And one important thing about displacement, it is a vector quantity. Okay, so we might write displacement as delta x. So delta, this just means change in, and put our little vector hat. Or if you're moving up and down, have delta y, also with a vector hat. And this delta, you can think of it as change in. So we always see change in. But what you really should think is final minus initial. Okay, so this is very specific. You always take where you ended up and subtract where you started. And so we denote this with subscripts. So delta x would be x final minus x initial. Our subscripts tell us which one we're talking about, whether it's final or initial. You might also see this written as delta x equals x2 minus x1, so your second position minus your first position. And then one that I use a lot, and it's very common, is delta x equals x minus x naught. And so if there's no subscript, that indicates some later position or some position later in time. And then x naught or x0 stands for your initial time, and the 0 stands for when time equals 0. So most of our problems start with the clock at 0, and then we start the stopwatch. And so the t equals 0 gives you x naught. Let's look at an example of displacement. Okay, so draw the number line. And let's just say this is x equals, actually let's put this x equals 1 meter. And this, maybe it's x equals 4 meters. And we have someone, and they're starting here. Okay, so this is time equals 0. And then they're moving to x equals 4 meters. Okay, the question is, what is the displacement? So they're obviously moving in x, so it's delta x. And I'm going to write it the way I typically write it, x minus x naught. So x being the final position, or 4 meters, minus x naught, the initial position, 1 meter, and we get 3 meters. Okay, so that's pretty simple, but what if we draw the exact same thing, except this time we're going to start over here. I'm not a great artist. So you start at x equals 4 meters when time equals 0, and you're moving to the left now. So now if we calculate our displacement, our final position x is 1 meter, our initial x is 4 meters, and we get a minus 3 meters. Okay, so this is the importance of displacement and it being a vector quantity. The sign of a vector always gives direction. Okay, it doesn't mean anything crazy. It just indicates direction. So you've moved 3 meters, and then the minus sign tells you you went in the minus x direction or to the left. Okay, so this is moving, or I should say, I don't know if he's still moving, but has moved in the minus x direction. Okay, so that's all that means. So it is perfectly okay to have a negative displacement. And in fact, you want to be careful to always get the signs right, because if your displacement should be negative and you forget that negative sign, you can get some wrong answers. So it's very important to recognize displacement as a vector and be careful not to switch things around and lose that minus sign. Let's compare two quantities that are often mistaken for each other. Okay, so distance versus displacement. Okay, so we've already talked about displacement, but what exactly is distance then? So distance is just the total length traveled. Always tempted to say total distance traveled, but distance is total length traveled. And a lot of times it may just be given the variable d. If something's moving in the y direction, maybe its height has changed, so that distance may be represented with h. And then displacement, again, is change in position. So displacement depends on where you started and where you ended, while distance only depends upon the total length. Okay, so distance is a scalar quantity, so scalar, and then we just discussed displacement as a vector quantity. Okay, so now let's do some examples to kind of illustrate the difference between the two. So say this is x equals 0, say 0 meters, and this is x equals 3 meters. And someone's here, They start at x equals 0. They move to x equals 3 meters, and this is where they stop. Let's calculate both distance and displacement. Well, the distance is pretty clear. They moved 3 meters. And the displacement, well, this is final minus initial, or they ended at 3 meters and started at 0. So their displacement is also 3 meters. So in this case, the displacement is equal to the distance. And so these cases are what makes it really easy to get them confused, because just because it's equal in this scenario doesn't mean it's always equal. So let's take a very similar example where you start from the same point, x equals 0, and you go to x equals 3 meters, but then you turn around and you come back. So you're going to start here and you're going to end here. So now your total distance, the total length you traveled, where you went 3 meters to the right and 3 meters to the left, so 3 meters plus another 3 meters, or 6 meters, your displacement, final minus initial position, well, you started at x equals 0 meters and you ended at x equals 0 meters, so your net displacement was 0 meters. Okay, so this is an example where your displacement can give very different results. It only depends on your final and initial position. So you can have positive, negative displacements, and you can move through some distance, but if you come back to where you started, your displacement is 0. Okay, so we can have many different answers for displacement. Okay, so now let's talk about maybe how fast our position is changing. So let's look at average velocity, and we also want to look at average speed, because they're not quite the same things, in the same way that displacement and distance are not the same thing. Okay, so our average velocity, well, velocity is a vector quantity, and it's going to equal our displacement, which is also a vector quantity, divided by the time. So how much did our position change divided by how long we were moving. Okay, and then average speed. Speed is a scalar quantity, so it does not have a direction. And this is just, you can think of it as how fast you're going in any direction, or the total distance divided by the time that you were moving, okay, or total time. So the way we write this as an equation would be, again, velocity is a vector quantity, so we put a vector hat, and I'm going to put a little x subscript to indicate it's in the x direction. So we take our displacement, delta x, divide it by our time interval, so maybe specific time interval or elapsed time. And so again, we can expand these deltas. This would be x minus x naught over t minus t naught, or if you prefer, x final minus x initial over t final minus t initial. You could have x2 minus x1 over t2 minus t1. That would be okay as well. And so we can take the units of displacement over the units of time, and that will give us meters per second. So length per time, meters per second. So let's look at an example. So average velocity. So again, we have our x number line, equals 0. And maybe we give some more distance, x equals 100 meters. So we have somebody and they're running, start at x equals 0, and they go to x equals 100 meters, but now we need some time information, so maybe they start here at time equals 0, and then they're at x equals 100 meters when time equals 50 seconds. Okay, so this would be our x naught and our t naught. Okay, so our average velocity, the x direction, delta x or delta t. Okay, occasionally I may drop these vector hats because we're only moving in one direction. So it's kind of understood which direction that we're moving in. So this is x minus x naught and t minus t naught. Or we ended at 100 meters, started at 0 meters, and we ended after 50 seconds and started when the clock was 0. So this would be 100 meters over 50 seconds, and that would give us 2 meters per second. Okay. And then obviously our distance was 100 meters, our time was 50 seconds, so our average speed was the same, 2 meters per second. Okay, so speed, average speed also 2 meters a second. Okay. And then let's do something similar to what we did with displacement. And start at x equals 0. And we're going to go to 100 meters. Then we're going to turn around and go back to 0. Okay, so maybe I write this way. We start at time equals 0 seconds, and then we get back at time equals 120 seconds. Okay. Now we can calculate average velocity, delta x over delta t. Well, same as displacement, we ended up at x equals 0, and we started at x equals 0. So this is just going to be 0 minus 0. And the time interval really doesn't matter, because we have 0 in the numerator. Okay, so this is 0 meters per second. Okay, that really doesn't feel right. Okay, but what about average speed? Well, this is just the total distance over the total time. Or we want 100 meters to the right plus 100 meters to the left. So that was 200 total meters over 120 total seconds. And so that is 2.4 meters per second. Okay, so this is really how fast we were going, but because we spent half of our time moving right and half moving left. Remember, when we consider speed, we don't consider direction. But because velocity is a vector, we have to consider the fact that we're moving right half the time and left half the time. So on average, we're not moving at all. And that makes sense, because if on average we weren't moving at all, we should expect to end up in the same spot that we started. And that's exactly what happens. Okay, so hopefully this builds a little intuition for what the difference is between speed and velocity. So now we want to graph position and velocity as functions of time. So position and velocity, which is time. So I'm going to put x on my y-axis and t on my x-axis. Okay, and so let's just start with this graph. If this is a flat horizontal line, so this means my position here is the same as my position some time later. And so this represents an object whose position is not changing. Okay, so if it's not changing, it's another word of saying it's not moving. And also notice the slope is equal to 0. Okay, well now if we wanted to get our velocity versus time graph, well first I want to look at my equation for average velocity. This was delta x over delta t. And if I write this in this way, x2 minus x1 over t2 minus t1, you should recall from algebra that the formula for slope of a line, when we have y versus x, is y2 minus y1 over x2 minus x1. Okay, so if we had y versus x, then this would give us the slope of our line. And so this is the slope of position versus time. And then, so this means that our velocity should equal the slope. Okay, so if the slope of our position versus time graph is 0, then that means that our velocity should also be 0. Okay, and since the slope is 0 everywhere, the velocity should be 0 everywhere. And this should make sense because if your velocity is 0, this means you are, again, not moving. And that's exactly what we said was going on in our position versus time graph. So let's do another one. So maybe we have a position that's changing like this. So now our position gets more positive. Okay, and since we said the slope is important, its slope is, number one, is constant, which means it's the same everywhere, and it's also positive, so a constant positive slope. Okay, so now let's look at our velocity versus time. We said that the slope of our position versus time would equal our velocity versus time. So this is a positive slope, so that means our velocity versus time will be positive. And since it's constant or not changing, that means our velocity needs to remain positive and remain the same value for all time. So again, we have a horizontal line, but now it's shifted up. Now it's not 0, it's some positive number. Okay. Okay, and this is a constant positive velocity value. Okay. Let's do another one where maybe our position is going down now. So maybe we start here and go down. So here again, the slope is constant everywhere. So whatever the slope is, it doesn't seem to be changing, but now it's negative. So a constant negative slope. And so this just means, well, it's starting at a positive x value, and then it's going closer and closer to 0. And then once it passes 0, it gets more and more negative. So it's just seems to be moving in the minus x direction. Okay. if we plot velocity versus time, well, again, this is a negative slope, so that means our velocity has to be negative, and it's negative everywhere and it's not changing, so that means our velocity should be negative everywhere and its value should not change. Okay, so this is a constant negative velocity value. Okay. And so one thing I don't want you to get confused about is I've been using constant on both sides. On the position versus time graph, the slope has been what's constant. On the velocity versus time graphs, the value has been constant. Okay, so constant means it's not changing. The slope is the same everywhere on our position versus time graphs, and that means that our velocity values are what should remain constant on the velocity versus time graphs. Okay? So we've been talking about average velocity, but what if we want to know the velocity at some moment in time? Well, this is called instantaneous velocity. Velocity at some moment in time, or at some instant. There's a moment in time. And typically you would need calculus to define this really well, but we can get something that's kind of good enough just by looking at a position versus time graph. Okay, so say our position changes something like that, and so, oops, we have position at some point, and maybe it changes to some other value. So at t1 we have a value x1, and at t2 we have a value x2. And if we wanted to find the average velocity, we said it's just the slope of these two lines. So delta x for delta t, or the change in x, the change in time. So we can take these 2 points and find the slope, and that represents our average velocity. But then we can ask, how fast are we going at t1? And so if the slope represents the velocity, we need a way of finding the slope at t1. And so what we do is we imagine taking this point at t2 and bringing it closer to t1. And so if this represents our time interval, we want to make delta t as small as possible by bringing these points closer together. And then as we bring our points together, notice the slope is also going to come together. It's going to approach the slope at the time t1. And so if you imagine bring t2 close to t1, you kind of have to visualize this as much as possible. It may take a little bit of practice. And then you want to find the slope at t1. And the reason why we have to visualize this is because if t2 equals t1 exactly, then this would equal 0. t2 minus t1 would be 0, and we're not allowed to divide by 0. Okay, and so in calculus, this is called taking the limit. So we want delta t, this time interval, to go to 0 by bringing these two together. And when we do that, we get the slope at t1, and that represents our instantaneous velocity. Okay, so if you imagine our position graph, and you were to draw a line that represented the slope at t1, this is called a tangent line. Tangent lines only touch at one point, so it's only touching at t1, and it gives the slope at that single point. And so the slope at a point of a position versus time graph, it also represents the instantaneous velocity. Instantaneous velocity. Okay, so now let's practice this. Let's see if we can get a better grasp of it. Okay, so let's draw position versus time graph that looks like what we just had. Okay, now I want to take a bunch of points. Not too many, not too close together. Okay, but I want to imagine drawing the slope at each one of these points. Well, the slope, or a line that would just touch at one point, start off with a really small slope. And then as we move from point to point, our slope is increasing. Okay, so the first thing to notice is that the slope is increasing. Well, since the slope represents our velocity, that must mean our velocity is increasing. So down here, close to 0, the slope is really close to 0. So that must mean our velocity is close to 0, pretty small. And then since the slope is increasing, the velocity must also be increasing. Okay, so the velocity is increasing. Okay, let's try another. So maybe you start off like this and go like that. We can just take a bunch of points, and maybe up here it's pretty flat, so the slope is roughly 0, and then it starts to get more and more negative. Okay, actually let me do it right here. Velocity versus time. And so again, we said our velocity is starting roughly at 0 because the slope is 0. Okay, slope is roughly 0 here. It's roughly 0. And then it looks like slope is decreasing. So that means that our velocity should start at 0 and then it should decrease. Okay, so velocity is 0 and then it decreases. Alright, so now let's talk about acceleration. So we've had our velocity changing. So let's talk about acceleration. So acceleration is the change in velocity, or how much velocity is changing with time. And so average velocity would be, or average acceleration would be defined in much the same way as average velocity. So again, we're moving in the x direction. So this would be the change in velocity over the change in time. Okay, since we're talking about acceleration in the x direction, put our x's, and these are vector quantities. Okay, so technically they should have a vector hat above them. And again, I'm going to write this as v minus v naught, or vx minus v naught x, and t minus t naught. Okay, and so the first thing you should recognize is we have this thing that looks like a slope formula again. Okay, so this time it's the slope of velocity versus time. Okay, so let's draw a velocity versus time graph, since we just got some of those, and see if we can't get an acceleration graph. Okay. So if our velocity starts off positive and remains positive, so zero slope. Since our velocity value is remaining constant, we may call this constant velocity. Well, since the slope is zero, that must mean our acceleration value is zero. And since it's remaining zero, acceleration should remain zero. So acceleration has a zero value everywhere. Okay, what if our velocity was going up? Well, oops. In this case, velocity is increasing, or positive slope. So since the slope represents acceleration, a positive slope means we should have a positive acceleration value. Keep doing that. So it starts positive, and since the slope is remaining constant, okay, it's going up the same amount everywhere, acceleration is constant. So this is a positive constant acceleration value. And so you can quickly see that just by knowing these relationships between position and velocity and acceleration and velocity, we can take a simple position versus time graph and immediately know what's happening in the velocity and the acceleration graphs. Okay, so acceleration, we said, is a change in velocity with time. So it has units. I always want to mention these. Since it's velocity over time, that's meters per second over second, or meters per second squared. Okay. And so meters per second squared is a pretty weird unit. So I like to go over what that really means. So what does it mean to have units of meters per second squared? Okay, so let's say that something is accelerating in the x direction, and it has a value of 10 meters per second squared. Okay, so I'm going to draw a really long line, and this is going to represent t equals 0 seconds, and then t equals 1 second, and this is going to be t equals 2 seconds, and then way down here is going to be t equals 3 seconds. Okay, and so say we have a car, and it's the one that's accelerating at 10 meters per second. So initially, the car isn't moving. So 0 meters per second. Okay, how do we figure out how fast it's going after 1 second? Well, it's convenient to write this as 10 meters per second per second. So this means if it's accelerating with 10 meters at 10 meters per second squared, its velocity is going to change by 10 meters per second every single second. Okay, so here, now its velocity has increased to 10 meters per second. Okay, so its velocity vector, if we draw it, now has some length to it, so 0 velocity there. Okay, what about after another second has passed? Well, now it should go up by another 10 meters per second, so now it's 20 meters per second. So the velocity vector is growing. Draw it longer. And you can imagine after 3 seconds, it's going to be going even faster. Okay, so now it's going 30 meters per second. Okay, so its velocity arrow is even longer. Okay? And so the reason why I spaced these tick marks out is because every second it's going faster and faster, so it should cover more and more distance. Okay, so even though this is a time graph, it's meant to represent that the car is moving further and further away in every second because it's going faster and faster. Okay, so AX equals 10 meters per second squared. This means your velocity in the X direction will increase by 10 meters per second every second. Okay, so anytime you have a weird unit, it's useful to think about what's actually going on and not let this scare you. It's really important that you get your units right, and it can help you solve a lot of problems, but you should also have some intuition for what this means. Okay, so now that we have velocity and acceleration, I want to talk about their relative directions. So velocity, acceleration, directions. Okay. So maybe at t equals 0 seconds, we'll do 4 different times so we can see how they affect each other and how they change. Say we start off with a velocity vector moving to the right, and our acceleration is in the same direction. Okay, so now some time has passed. We were moving to the right and we were accelerating to the right. Well, that means that our velocity vector is even bigger. Okay, it increased because we were accelerating to the right. Acceleration vector is the same. After more time has passed, keeps growing. Maybe I should have drawn this a little bit shorter so I can keep up. Okay. And it's going to get real big at the end. Okay. Maybe these are all in the X direction. Okay. So what this means is when velocity and acceleration are in the same direction, the speed increases. So the length of the arrow represents the speed, or how fast it's going, and if they're in the same direction, then that speed should increase. Okay, so what if we start with velocity to the right, but our acceleration is to the left? Well, after some amount of time, our velocity vector is going to decrease. So it's going down, okay, because we're accelerating more to the left. And then if we keep accelerating to the left, eventually our velocity vector is going to be 0. Okay, we're going to stop. It looks like we're slowing down and we're eventually going to stop, but we keep accelerating. Okay, so now we're at a stop, but we accelerate to the left. So now our velocity is to the left. Okay, so the acceleration tries to make your velocity align with it. So if they are in opposite directions, first you'll slow down, so your speed will decrease, and then you will change directions. Specifically, you will go in the opposite direction. Okay, so you won't start going up or down, but if you were going right, now you will start going left. So we've been talking about situations where our position is changing, so we have some positive or negative velocity, and then we've considered changing velocity, so now we're accelerating. but we're not going to consider any changing acceleration because for the most part, in many cases, acceleration is roughly constant. So we don't have a whole lot of situations where the acceleration is changing, so we really don't have to get any more complicated than constant acceleration. Okay, so acceleration is roughly constant, we're not changing. Okay, so this means that our average acceleration is equal to our instantaneous acceleration since the acceleration value is not changing in time. So, with this assumption, we can obtain some equations and spell. We can get what's called kinematic equations or constant acceleration equations. And these are equations that we can use anytime the acceleration is constant. Okay, so the first thing is we also let t naught, or our initial time, we let it always be 0. And what this does is it makes it where delta t, which is normally t minus t naught, since t naught is 0, all we're left with is t. So everywhere we would have had a delta t, now we're just going to replace that with t. Okay? And in doing this, we're going to get these equations. So rather than derive them, I'm just going to write them because the derivations, they're not difficult, but it's a lot of algebra. Okay, so I'm going to write the equations you get. I'm going to write 3 of them that you typically use, and then there are 2 more that you sometimes see depending on the class you take. So this is the first kinematic equation, and it's just rearranging the definition of average velocity. So it gives you velocity as a function of time. Okay. Our second equation is one where you can get the position as a function of time. Okay, so position as, an abbreviate function. And the third is this one. And it is one that gives you velocity as a function of position. Okay. So the first one doesn't have position in it anywhere. The second one doesn't have your final velocity. So if you don't know your final velocity, you can use the second equation. And the third equation doesn't have time anywhere in it. So if you don't know anything about time, you typically go for the third equation to learn something about motion. Okay, and so I want to make a few quick notes. So first is I want to make a few quick notes. So first, we can replace x with y in any of these equations if, or maybe I should say for constant acceleration in the y direction. We'll actually look at a special case of that very shortly. Okay, and then there are often 2 other equations that are sometimes given, again depending on your class, and they look very similar. Okay, so this looks like the second equation, except now instead of v naught, you have just vx, so final velocity instead of initial. And instead of plus 1/2 axt, you have minus. So it's derived in very similar ways. You just do a slightly different substitution. And then we can use the mathematical definition of an average to get this equation. Okay, so these are not always given, but they are in some classes. And so if you notice, in each of these you're missing something. So in the second one you don't have final velocity. In this other one that looks very similar, you don't have initial velocity. And in this final one you don't have acceleration, which shows up in the other four. Okay, so no matter which scenario you get in, if you're missing something, you can still find an equation that allows you to calculate what you want. So now we're going to look at a special case of constant acceleration in the y direction, and that's called free fall motion. So objects that fall near Earth's surface, so falling near Earth's surface only under the influence of gravity, these objects will fall with gravitational acceleration. Okay, and that gravitational acceleration is constant. Okay, so near the surface of the Earth, that acceleration is 9.8 meters per second squared, and we give it the special letter g since it stands for gravitational acceleration. And the first thing to notice, it is a positive number, but when we drop things and they fall towards the Earth, they always accelerate downward. So the acceleration is in the y direction, and since that's negative y, the acceleration is minus g, okay, or minus 9.8 meters per second squared. So it's important to keep in mind that g itself is a positive value, but because we're accelerating downward, the acceleration is what is negative. Okay, so it's going, we're accelerating downward. Okay, should really say accelerate, accelerating downward. Okay, so now we can use our kinematic equations. Okay, so now we have a special case of constant acceleration. So we can go to our constant acceleration equations and plug in this value of g. Okay, so I'm going to write the constant acceleration equations and then show you what they become in free fall. So first of all, I'm going to write them all in terms of y. So everywhere I had an x, I'm going to replace it with y. So v naught yt plus 1/2 ayt squared. Vy squared equals v naught y squared plus 2 ay y minus y naught. Okay, so now if we use the fact that we know the acceleration in the y direction is equal to minus g, and we substitute, we can get our free fall equations. This one becomes Vy equals V naught y minus GT. This one, y equals y naught plus V naught yt minus 1/2 gt squared. And the last one is vy squared equals v naught y squared minus 2g y minus y naught. Okay? And so how do you know an object is in free fall? So I'll give you 3 cases. So first of all, we're still talking about objects moving in one dimension. So it's moving straight up and down. So that means something's only under the influence of gravity. It has either been thrown or launched straight up. Okay, so its initial velocity in the y direction is positive or greater than 0. The other case is it's thrown straight down. Or its velocity is less than 0 or negative. Okay. And then the last case is it's dropped. Okay, so you don't throw it up, you don't throw it down, but you just drop it. We typically call this dropped from rest. So what that means is the moment that it leaves your hand, or the moment that you drop it, however you drop it, the initial velocity in the y direction is 0. Okay, so in all of these cases, once the object leaves your hand, whether it's going straight up, straight down, or is just released from rest, the moment after it is released, it's only under the influence of gravity, and therefore it is in free fall. So in the next video, we're going to look at some examples and some problems going over not only constant acceleration, but the special case of free fall.